Okay, can you hear me? Hello?
Yes, we can hear you. Can you please share your slides?
Okay, of course, absolutely. Okay, I suppose you can see my screen.
Yes.
Okay, good afternoon. So first of all, I would like to thank the organizers for this opportunity to share these recent results. Just came up in a journal, and I am going to present here some probably something quite trivial to a lot of people at audience, but I hope you like anyway. Okay. Oops. Okay. This work, it was done in collaboration with some people, some from SUSTEC, from it's a group led by Diantam, and also in collaboration with some researchers in Brazil, Andrea Sagia and Marcelo Sandi, and Chankangu and Chilong, who led the experiments, did all the data analysis, and etc. Okay. So first of all, because I'm going to talk about quantum charging advantage, so it's important to mention some recent, not that recent, but very relevant results on this subject. So the idea is, how can we quantify or testify or check whether we have or not quantum charging advantage? Okay, so the point is, what is quantum and quantum battery? Okay, and probably many of you already know this works by Campaoli and by Jim. So it's a 2PRL from some years ago, in which they replied and proposed many different ways to quantify what is quantum in a quantum battery. Okay, so the idea is that with two very simple parameters called quantum advantage parameters, they defined that in some rules that you have to satisfy to argue that in fact you have some quantum charging advantage. Okay, to avoid a kind of fake advantage, you know. So we need some really quantum to have some advantage. Okay, and we need parameters to check if this advantage is quantum or not. Okay, because sometimes the quantum charging is better because you are spending a lot of energy charging your battery. Okay, so one relevant result in this last PRL by Jim is that, unfortunately, to have this extensive quantum advantage, so very nice scaling, we need many body interacting system. And this many body means that you need n body Hamiltonians. For example, this PRL is an example on how to define what I mean by n body or k body. Okay, so in fact, you need any body Hamiltonians like this, and you also need all-to-all interactions. So you need very complicated Hamiltonians to have this extensive quantum charging. So what we wondered is that, okay, assuming that this cannot be, it's not easy in the experiment, how can we achieve this quantum advantage, okay, without these global operations? So the idea is trying to find a Hamiltonian that satisfies the conditions for quantum advantage, which is this gamma parameter related to the power and this eta parameter related to the cost to implement the Hamiltonian. Both of them has to be higher than zero. So how can we, what kind of Hamiltonian can give us this advantage? Okay, so to address this problem, we used one of the most promising platforms to create some exotic or complicated interactions. Okay, so superconducting qubits, they are still one of the best platforms. Okay, so basically what we have, there are transmon qubits. Okay, in the experiment, these transmons, they are characterized by the transition frequency, but also an harmonicity term that makes possible to truncate each qubit, each transmon as a two-level system. Okay? And we have this very nice tunable interaction. Okay, so we can connect two transmon qubits using a kind of transmon coupler. And this transmon coupler, through external driving flux, we can turn off and turn on interactions between the qubits in the system. Okay? So the kind of Hamiltonian we try to engineering is a kind of flop-flop Hamiltonian. Okay? It's not a flip-flop Hamiltonian, so it's a two-photon transition Hamiltonian, which is quite complicated to engineering, but in principle, it can be nicely done in superconducting qubits, just applying a highly oscillating flux in the coupler that connects two qubits. So with this high oscillating frequency, high frequency flux, we can engineering kind of interactions that mimics a two-photon transition. So for example, this can be relatively well done for two qubits. So we see this transition from the total ground state to the two excited states. So it's a kind of anti-blockade mechanism, okay? And in principle, this can be scaled up for more qubits. So in the controllability is relatively high. And in this case, we are able to check that conditions that I mentioned before in a very specific example. Okay, so basically, here we consider a 5-cell quantum battery. So in principle, this can be done if you turn off effectively the interaction between many of the qubits and just turn on interaction between some specific qubits. So this can be done, as I said, using this flux line here. In this case, because we have this interaction, this is the quantum charging, okay? Because we have an interaction, and in principle, entanglement can be created in the system. But we have to compare our results with the full classical case. So what do I mean by full classical charging? The full classical charging is related to the quantum evolution. It's not exactly related to the system itself. So if you have interactions and you can promote entanglement in the system, you say that this is quantum. If you don't have any interaction, so you don't promote any interaction or any entanglement, and the qubits, they evolve independently, you say this is classical. So the idea is quite simple. Okay, so using these two kind of control, we can compare what happens if you charge the system collectively or if you charge the system just as a classical device, as a classical battery without entanglement. So in this first experiment, what we did is a check of this energy cost charging, okay? So as I said, the eta parameter is related to the energy cost. So this quantity has to be higher than 1 because we need that the quantum charging expends less energy than the classical one. At the same time, the gamma parameter cannot be smaller than 0 because it means that the classical charging is charging faster. So what we need is operate in this region in which both parameters, they are higher than 0. So we can check what happened if you have a small alpha parameter. This alpha is the quantum control in the classical battery, okay, because it's a parameter that you can easily change, so you can control it quite effectively. And this is the point, because here, if you have, for example, alpha of order of 0.4, you have a very good advantage for the quantum battery, but this is because you are spending more energy, okay? So we have to cross this line to have some good advantage as well, but without spending more energy. So as a comparison to check what is going on during the evolution, we can see this high peak for the quantum power because of this two-photon transition that we can promote using this effective Hamiltonian theory. Okay, and of course, the idea is that you can scale up the system to more quantum cells. So we were able to optimize, doing some optimization, and run the experiment up to 12 qubits, and the results look like this because um, we need to, for each size of the battery, we need adjust buff parameters. We need to compute the effective G coupling, and also we need to adjust the alpha parameter to make sure that we always spend more energy in the classical charging than in the quantum one. Or in the worst case, as we show here, for example, for some points here, in the worst case, these two guys, they spend exactly the same amount of energy, okay? And in these two cases, we still have some quantum advantage. And yeah, okay. So the last point that we try to, sorry, in this case, checking all those parameters to make sure that we have a fair dynamics between the two cases. So they spend the classical always spend more energy than the quantum case. We check what happened when we increase the battery size. So we can see that we have some increasing in the power of the system at the same time that we also compare the eta parameter for different size. And to see what is going on and actually make sure that this two-photon transition is the main mechanism to charge the battery faster, we compute the atomic G2 function, which is quite simple, which is basically, it's a correlated to photon excitation, okay? And this correlated to photon excitation actually agrees quite nicely with this advantage increasing in the system. So we can see that in all cases, we have a very high two-photon correlation transition for shorter times in the time scale of the maximum power for the battery. And of course, for longer times, this correlation decrease because the system gets a lot of population. Okay. And as a check, just to see what is going on with entanglement and coherence in the battery, to check this the quantum side of the battery, we also study the incoherent and coherent work, okay, as defined some years ago. And we see as well a nice scaling of both the incoherent and coherent power, okay? So computing, for example, the advantage for both quantities, we can see that they still are above the zero as expected for quantum advantage, is still keeping the same ratio of energy cost between the classical and the quantum case. Okay. And to see, to check what is going on with the entanglement in the system when you increase, we also computed the second order Rayleigh entropy, which is quite nice to measure entanglement. If you do this bipartitions and you take the average. So if you do it, this quantity higher than zero means that we have entanglement in the system. So to measure this second order Rayleigh entropy, we have to use random measurements in the system to approximately compute the Rayleigh entropy, because we have 12 qubits and doing tomography in these 12 qubits is absolutely hard. So doing this random measurements, we could see that the theory and the experiment, they agree quite nicely, okay? And then we can see that the increasing in the entanglement when we increase the battery size. So this increasing is almost linear, but we can see that we have some enhancement in the entanglement generated in the system. In contrast, we measure the entropy for the classical case, and as expected, it remains absolutely zero up to some noise. And as a take-home message of our work, we would like to emphasize this study. In this study, we always care about how much energy you take to charge a quantum battery compared to the classical one, because this is a proposal by that PRLs I mentioned before, that you always can charge a battery faster than a classical one, but sometimes you spend more energy. Okay, so the idea is how to keep this constraint and still have some quantum advantage. So in this work, we proposed an experimentally feasible way to do it using this two-photon transition. We implemented it as well in a superconducting qubit because, I mean, it's a good platform to test this kind of exotic Hamiltonians. Okay, so of course, as a open questions, we always have to check what happens in the thermodynamic limit, and as well checking what are the best scalings we can get if we always impose these experimental constraints. Okay, so I mean, the point is that because these all-to-all n-body interactions are really complicated, the question is what we can do with the available interactions in an experiment. Okay, and of course, this relation between quantum advantage and entanglement quantum operation, it is something that could be quite helpful to understand, to see what is going on, if entanglement is really critical for quantum advantage or not. Okay? So that's all. Thank you, everyone. I hope I said this inside the limit. So thanks everyone for the time, and thank the organizer for the opportunity.
Okay, thank you for this nice presentation. Do we have quick questions from the audience?
I have a question. So sometimes I'm a bit polemic on the quantum batteries fields. I was wondering, you say that entanglement is the source of the advantage. However, what is the difference in taking 2 qubits and using global operations, or taking one, how is it called, Q-treat, like 4-level system, and using local operations? Wouldn't the result be the same? Wouldn't you have the same super extensive advantage?
Good question. I mean, what I mean is that in principle, for example, as an open, some open question here, I mean, the relation actually between advantage and quantum entanglement, to me, is not also clear. What we always do is that if we have this quantum charging, we always check if we have entanglement, because it can be an indicative that the battery is really quantum, you know, so because you are using interaction and you have some kind of collectivity. So a signature of this collectivity is entanglement. If you cannot see some entanglement appearing in the system, there is something strange with the collectivity of your system. As the question about the considering all-to-all 2 qubits in a 4-level system, this is actually a good question. I never thought about that, to be honest, because in principle, if you have just one multi-level system, for example, in principle, you can charge it using a single classical field. And I'm not sure whether this is too different from a 2-qubit system. The point is that what is the energy cost involved in considering the Hamiltonian I am doing here with the charging Hamiltonian for a 4-level system? Okay, so we have to compare these two things. So for example, if you conclude that using a 4-level system, using less energy, you can charge the system faster than the quantum version. So I agree with you. So we have, at least here, we have one example that we have a better classical battery because there's no entanglement. But in principle, there is coherence. Okay, so someone also still can, we always have to compare things assuming that you could have coherence, but not entanglement. This example you are considering looks to me that it's a good thought experiment to do it. But I don't know if the four-level system charges faster than the quantum under this energetic constraint.
Thanks a lot. Very interesting. I'll contact you about this.
Okay,
thanks.
great.
Thanks a lot, Alan. Let's thank him again.
Thank you, the organizers. Bye-bye.
And our next